Hi everyone, good evening. This is actually take 2 of this video over the pyruvate to acetyl CoA transition step. So there's a biochem test soon, so I'm going to start making these videos again over just the reaction steps and then going through the lecture slides that the professor provided and only pulling out whatever was highlighted for the test. So with that being said, we're going to go over in this video the pyruvate to acetyl CoA step. And the enzyme that is used, we actually have a complex. We have the pyruvate dehydrogenase complex, or the PDH. The PDH needs 5 coenzymes in order to function. And the first 3 of these coenzymes would be TPP, which is like thiamine. We also have lipoic acid and FAD. Now, TPP, lipoic acid, and FAD, these are prosthetic groups, so that means that they're going to be bound to the enzyme at one point. We also have NAD and CoA as the final 2 of our 5 coenzymes. So NAD and CoA, however, are co-substrates, like how TPP and lipoic acid were prosthetic groups, while the final remaining 2, the NAD and the CoA, are actually co-substrates. They're all still coenzymes, though. Alright, let's walk through the steps. Again, we're dealing with a pyruvate dehydrogenase complex. This complex has 3 enzymes in it, so if we're going to be referring to things such as E1 and E2, we're not talking about the type of reaction here. We're talking about enzyme 1, enzyme 2, enzyme 3, like that. Okay, so the first step. So we have our pyruvate. We're going to use decarboxylation on this pyruvate molecule. We also need our prosthetic group TPP, and we're going to then form hydroxyethyl TPP as our main product here. But also we're going to release some CO2 in this first step. We need enzyme 1 in this step as well as the TPP. Enzyme 1 is known as the pyruvate dehydrogenase, so we're going to be using a dehydrogenase in the first step of pyruvate to acetyl CoA. We'll go into enzyme 2 in a bit, but in step 2, we're going to still have some of our enzyme 1 in play. So step 1 was decarboxylation of pyruvate with TPP to form HETPP, also known as hydroxyethyl TPP, as well as CO2. Now, we're going to oxidize in step 2. We're going to oxidize an aldehyde into a carboxylic acid. When we do this, remember, this complex, they're all together. This is to prevent any of these unwanted side reactions, and it just happens in a very efficient method. So, when we're talking about enzyme 1 and enzyme 2, remember, they're really close to each other. So, the oxidation of this aldehyde to carboxylic acid will create this reduced lipoic acid on enzyme 2, as well as this molecule having the name acetyl lipolysine. Well, acetyl, that's notating this other process here that's going on in step 2, where we have the acetylation of the lipoic acid. So, since we're going to transfer that acetyl group to the lipoic acid on enzyme 2, we're going to be using the transacetylase. That's enzyme 2, transacetylase. We're going to have this thioester bond. Going to be making a thioester bond when we move that acetyl group over to the lipoic acid. More on lipoic acid in the video over like the lecture notes and trying to shift through what the professor wants us to actually remember. Alright, step 3. This is where we're going to be making acetyl CoA. So we have our CoA, which is, again, a co-substrate. CoA is going to introduce that CoA part of that molecule. We have this SH as well on this coenzyme. So this is going to interact with the acetylated, sorry about that, I spelled that wrong with the T at the end. Okay, the acetylated lipoic acid. when CoA and the acetylated lipoic acid come into contact, and there's the enzyme number 2, which is the transacetylase. This is going to form our acetyl CoA. Remember, the acetyl CoA, this is what we actually need in the Krebs cycle. So we've turned pyruvate into acetyl CoA. We're also going to have the fully reduced lipoic acid now. And that's a problem, because we need to go back to the oxidized form of lipoic acid in order for the transition step to continue again if we need it. So step 4 and step 5 will help us solve that. So again, step 3, we're taking CoA plus the acetylated lipoic acid, and we're going to be using that transacetylase, and we're going to be making acetyl CoA and a fully reduced lipoic acid. We're going to have to restore this, also known as we're going to have to oxidize this again in the next couple of steps. There's a way to regenerate it. Alright, step 4. So step 4, we're going to take our fully reduced lipoic acid and we're going to take FAD. It's another one of our coenzymes, and this is going to be worked on by our third enzyme. The third enzyme in the PDH complex will be our dihydrolipoyl dehydrogenase. So it's another dehydrogenase step. When we use the dehydrogenase on the reduced lipoic acid and we have FAD present, we're going to be forming our oxidized lipoic acid as well as FADH2. Right, so this oxidized lipoic acid is where we started before step 2. So in E2 or enzyme 2, we need the oxidized form of lipoic acid. Then it gets acetylated in step 2. And then in step 3, it's going to be fully reduced when we do make the acetyl CoA. So therefore, step 4, we're able to regenerate an oxidized form of the lipoic acid via FAD getting a hydrogen using the dehydrogenase. Right, that FADH2, we're kind of in the same ballpark here. We need to get this back to the oxidized form of FAD. We need to regenerate it into its oxidized state. So how are we going to do that? Well, in step 5, we could take our reduced FADH2, and we're going to take this with NAD. That's our last coenzyme for the PDH complex. And we're going to use a dehydrogenase. We're going to use E3, enzyme 3 again, the dehydrogenase. And when we use the dehydrogenase, the NAD is going to pick up that hydrogen. So the results of this would be NADH and our regenerated FAD. This is again the oxidized form that we needed to be regenerated. So step 4 will regenerate the oxidized form of lipoic acid, whereas step 5 will regenerate the oxidized form of FAD via NAD. In summary, we're going to decarboxylation of pyruvate with TPP. That's going to involve the enzyme 1, which is a dehydrogenase. We're going to get HETPP plus CO2. Step 2, we're going to take our oxidized lipoic acid and we're going to acetylate it. So we're going to need a transacetylase as well as the dehydrogenase to complete that. In step 3, we're going to mix CoA and the acetylated lipoic acid. We're going to use that transacetylase, or enzyme 2 again, and we're going to actually get our acetyl CoA, as well as a fully reduced lipoic acid. The lipoic acid needs to be regenerated into its oxidized state. So in step 4, we're going to use FAD and the dehydrogenase. To remove those hydrogens, we're going to reform the oxidized lipoic acid, and we're also going to get FADH2. Alright, so now we need to regenerate FADH2 into its oxidized state. So we're going to take the reduced form, FADH2, we're going to have NAD present, we're going to use enzyme 3 again, dehydrogenase, a second dehydrogenase, or enzyme 3. And then the hydrogen will be transferred to NADH, and then we have regenerated our FAD. And then this just goes in a big cycle if there's more pyruvate. Alright, let's talk about transition regulation. So regulation of this transition step will be involving the phosphorylation, spelled that wrong, sorry about that, of the enzyme 1, or E1 dehydrogenase. Alright, when we phosphorylate it with ATP being present, this will make it inactive. So when it's phosphorylated, when the dehydrogenase, the enzyme 1 dehydrogenase, is phosphorylated, when ATP is present, that will make it inactive. Okay, so we're going to use this enzyme here. We're going to be using a PDH kinase. When ATP is present and when we need to phosphorylate the E1 dehydrogenase of the complex, we're going to be using a kinase to add those phosphate groups, and it's going to inactivate it. Therefore, the opposite is true. When we dephosphorylate the enzyme 1, aka the dehydrogenase, and this is going to occur without ATP present, or when there's no ATP, this is going to make it active. The enzyme here will be a phosphorylase. So to dephosphorylate the E1 dehydrogenase, when there isn't any ATP, when we want to make it active, we use the PDH phosphorylase to remove those phosphate groups, and then now enzyme 1, aka the dehydrogenase of the complex, will be active, and we start converting the pyruvate into acetyl CoA, so it could go through the Krebs cycle and start generating the electrons needed for electron transport and all the other carriers and whatnot. So we fully oxidize it and we get some ATP in situation 2 here when we dephosphorylate the dehydrogenase. Alrighty, that's going to be it for this one. Please take care of yourselves and do something nice for someone.